All right, so let's jump back to that question that we actually started this section with, namely this question of actually trying to come up with an efficient or easy to use way to actually compute some of these massive powers, reduce modulo whatever number we're actually going to be dealing with. This again is going to be one of these super crucial steps in this world of this RSA crypto system, because if I don't have an efficient way to actually do this modular exponentiation, this whole process actually breaks down. For example, if you think about what Alice actually has to do, if Alice is going to try to send you some special message X, what she's going to do is she's going to take that message, she's going to have to compute that thing raised to some power E that you told her to use, and then reduce that thing modulo whatever modulus N you told her to use. If she doesn't know how to actually compute that thing or have any ability to do that efficiently, this whole process would break because she wouldn't be able to actually send you information because she does not actually know how to encode all of that stuff. The idea is that she knows what she's supposed to do, but if she doesn't actually have the computing power to actually do that, the whole thing would be essentially worthless. So what I want to do is I do properly want to come up with some efficient or easy to use way to actually do this modular exponentiation. So what I'm going to do in this case, I'm actually going to run it on a few somewhat toy examples so we can really start to see how this algorithm is going to come into play. And then once we actually know what's going on, we'll actually go ahead and see the coding of this thing and then really try to feed some very large powers into this thing and actually see that it's actually a pretty quick process to compute out some of these moduluses. So in this case, we're going to start this thing by actually looking at the example of taking the number 3, raising that thing to the 23rd power, and then reducing this thing modulo 25. So in this case, you could actually just simply take 3, raise it to the 23rd, plug that thing into a calculator. It's going to kick out something really big. You can take that number, divide it by 25, and just simply record what the remainder is going to be, and you'd actually know what that answer is going to be. In that case, that's going to be a fine and dandy way to attack it with small numbers, but it becomes horribly inefficient the moment those numbers become of any substantial size. By simply taking that 3 and changing it into a 3,333 and taking that power of 23 and raising it to, let's say, the 23 millionth power, you can simply see that evaluating that massive thing is no longer feasible because you're quickly going to break your computer by trying to take something raised to the 23 millionth power. So what I want to do is I want to actually come up with a way that it's actually going to do this reduction as I go. So it's going to be this very nice notion of building things up and then constantly reducing. Because at the end of the day, I'm going to be kicking out some number between 0 and 24, so I might as well start to see those numbers as I go. The idea is that anytime I'm going to kick out a number that's going to be larger than 25, I can simply reduce this thing back into this world of 0 to 24 as I go. The way that I'm going to be doing is actually by taking this exponent 23 and breaking that thing up into a whole bunch of powers of 2. So the idea is that 23 can be viewed as a 16 plus a 4 plus a 2 plus a 1 in this case is really going to help me see how to take this number 3 and start raising it to smaller powers that are essentially all going to add up to this value of 23, giving me this power of 23. So that's really going to make this whole thing tick, is that you're going to view this exponent as powers of 2 and then build these powers as I go. So what do I mean by build these powers? It's going to be this idea of looking at the first state, which is going to be taking 3, while raising that thing to the first power, which is simple enough. It's simply just going to be a 3, which I know is going to be congruent to 3 in this modulo 25 world. What I can do next is I can build up powers of 2. I know that 3 squared is actually going to be that previous step of 3 to the 1, and I'm going to be squaring that thing. And then the last step, I know that 3 to the 1, well, that's simply just going to be a 3. So that's going to tell me to take a 3 squared, which is going to kick out a 9, and a 9 doesn't have to be reduced. It's just simply going to stay as a 9 mod 25. What's going to happen next is I'm going to see this 3 raised to the 4th power. What's going to happen is that 3 to the 4th is actually viewed as a 3 squared squared. So here's the idea that 3 squared is actually going to be the 9 from the last step. And then I'm still going to be squaring this thing, which is then going to turn into an 81. And an 81 now actually can be reduced. An 81 modulo 25 is going to kick out a 6, because I can see that there's going to be a 75 hiding inside of 81. So I know that 81 minus the 75 is going to turn into a 6, and at the end of the day, that's still being done mod 25. Okay, so we're going to continue this process by seeing a 3 to the 8th. Well, a 3 to the 8th then is viewed as a 3 to the 4th squared, because 4 times 2 is going to give me that value of 8. So here's where we're going to use that previous step. So this is this idea of building these powers up. The idea is that once I know 3 to the 1, I can compute 3 squared. Once I know 3 squared, I can compute 3 to the 4th. Once I know 3 to the 4th, I can compute 3 to the 8th. So 3 to the 8th is going to be 3 to the 4th, i.e. my previous answer, which is a 6, and that thing's going to be squared, which is now going to kick out a 36. and a 36 reduced mod 25 is going to turn into 11. Okay, so let's keep on going. So I'm going to have 3 to the 16th, which is then going to be a 3 to the 8th, and that's going to be squared. So 3 to the 8th is going to be that previous step, which is an 11, and you're going to square that thing, which we know is going to kick out a 121. And if I reduce 121, it's going to turn into a 21 mod 25. What I'm going to do is I'm going to keep on going. I actually wouldn't have to go any higher, but I'm going to try to see a few more examples, so I'm going to go a little bit farther. So a 3 to the, let's say, 32nd, which I know is a 3 to the 16th, and that's squared. Well, 3 to the 16th is going to be that last step, which is a 21, and that's going to be squared. 21 squared in this case is what? Something like 441. And then if I reduce that thing modulo 25, it's going to kick out a 16. So then I can go up another step. I'm going to have 3 raised to the 64th power, which I know is going to be 3 raised to the 32nd squared. Well, 3 to the 32nd is that previous step, which is that 16, and that's going to be squared. And 16 squared is going to be 256. And if I reduce that thing modulo 25, that's going to kick out a 6, and that's going to be mod 25. So in this case, you can see that you can build up these powers of 3 as I go. So I get 3 to the 1, 3 squared, 3 to the 4th, 3 to the 8th, 3 to the 16th, 3 to the 32nd, and then 3 to the 64th. All right, so now that I have these kind of massive little laundry list of all of these powers of 3s that I want to deal with, what I can actually do is I can actually go back to actually trying to compute what is 3 to the 23rd power and then reduce that thing mod 25. So here's the idea that I'm going to take this number 23, break it up into its base 2 representation, and then use all of these little building blocks as I go. So if I sweep this forward a little bit, what I'm going to see is 3 raised to the 23rd power is going to be viewed as a 3 to the 16 plus a 4 plus a 2 plus a 1. So here's the idea is that 23 is going to be a 16 plus a 4 plus a 2 plus a 1, which is to say a 2 raised to the 4th. There's not any cubic term. There's not an 8 in that little list. So it's a 0 times a 2 cubed plus a 1 times a 2 squared, that 4, plus a 1 times a 2 plus a 1 times a 2 to the 0. That is to say that the number 23 viewed in the binary world is going to be a 1, 0, 1, 1, 1, and that's base 2. So the idea is that that single 0 is going to come into play when I don't have an 8 in this list. So the idea is that everything else is actually going to be represented except for that 8 is not there. So that's why I have that little missing spot or that little 0 in that little binary representation of 23. Okay, so let's go back to this example of actually seeing 3 raised to the 23rd power. What that's going to tell me to do is by using some properties of exponents that this thing is going to actually break up into a 3 to the 16th multiplied by a 3 to the 4th multiplied by a 3 squared multiplied by a 3 to the 1. So now the idea is that all of those little pieces, the 3 to the 16th, the 3 to the 4th, the 3 squared, and the 3 to the 1, I know what all of those things are going to kick out in this mod 25 setting. The idea is that 3 to the 16th, I know is simply going to turn into a 21. A 3 to the 4th, I know turns into a 6. A 3 squared is going to turn into a 9. And then that value of 3 is simply just going to be a 3. And that's got to be done modulo 25. So what you could do at this stage is you could simply take this big product of 4 things, multiply it all out, and then actually reduce that thing mod 25, because it's not going to kick out a very large number. That's great and dandy, except for, again, the moment this 23 becomes something massive, I'm going to have a whole bunch of terms in this exponent list because I may have a gigantic number and it's going to have a lot of components in this binary representation, so I may not want to multiply out 10,000 things at this stage. So what I'd like to do is I'd like to come up with some systematic way to actually build these things up as I go. So again, here we're going to have this idea of chunking this thing into little tiny, smaller, manageable pieces. In the exact same way that we built up these powers of 3, I'm actually going to be doing this multiplication as little tiny groupings. It's very similar to this idea of how do you actually compute some of these factorials. You go ahead and compute the first couple numbers, then you multiply by the next one and the next one and the next one. It's going to be the exact same thing happening here. The idea is that I'm going to work from the right side over to the left side. And I'm going to go ahead and just bring out the kind of fully written out version of this thing so I can kind of point to things rather than have to rewrite it as I go. So what we had in that previous slide was at this stage. So what I want to do is I want to group the 3 and the 9 together. The 3 and the 9 multiply to make a 27. And then I'm going to reduce that 27 modulo 25, which is going to kick out a 2. So you're going to constantly just be lumping together the last 2 things in this list. Whatever number that kicks out, you're going to reduce that thing modulo 25. So you're going to essentially take this group of 4 things, chunk it down to 3 things, chunk it down to 2 things, and then finally have it as one single little number at the final stage. So 9 times 3 is 27. That 27 turns into a 2. The 2 times the 6 then turns into a 12. That doesn't have to be reduced because it's not larger than 25 in this case. So then the very last step, you're going to take the 21 and the 12, multiply those together, kicking out a 252, finally giving you your final answer of a 2 in this situation. So that is to say that 3 raised to the 23rd power modulo 25 is simply going to kick out a value of 2. So if I want to see another example of this, what I can do is I can look at the number of, let's say, 98. What I can see is that 98 is going to be viewed as a 64 plus a 32 plus a 2. The idea is that the largest power of 2 that's going to exist inside of 98 is going to be this power of 6. So I have a 2 to the 6 coming into play. There's going to be a 2 to the 5th for that 32, and then that little last over bit simply is going to be a 2. So in the binary representation of this thing, I'm going to have a 1, 1, representing the power of 6, the power of 5. I don't have the 4, the 3, or the 2 occurring, but I do have that 2 to the 1 power, which is coming into play here, and then I don't have a little singleton 1 at the very end. So I'm going to have 3 terms coming into play to here because of those 3 little 1s that are coming up in that binary representation. Okay, so if I wanted to actually compute what 3 to the 98th power was modulo 25, what you're going to do is you're going to take that 98, explode it up into a whole bunch of little pieces. In this case, there's only 3 pieces. The 3 to the 64, the 3 to the 32nd, and then the 3 squared. If you reduce all of those things mod 25 using that little laundry list that we had earlier, that's why I went all the way down to 64 in this case. So if you take that 3 to the 64th, what's going to happen is that that's going to kick out a 6, the 3 to the 32nd is going to kick out a 16, and then the 3 squared is going to be a 9. So here's where you're going to chunk these things from the bottom of the list together. So the 9 and the 16 are going to multiply together to give you a 144. You reduce that thing mod 25, which is going to kick out a 19, and then you have those two things, you're going to lump them together to actually give you a 114, which is at the end of the day going to give you a final answer of a 14. So it seems like something that would be absolutely obnoxious to actually compute. Well, the idea is that it's broken up into 3 smaller little problems, this idea of computing those things, which are all actually built out of this idea of taking these powers of 3 and then getting them larger and larger as you go. Doing this reduction every single stage that you go. The moment something spills over 25, you reduce. Over 25, reduce. Constantly reducing as you go. Taking little pieces, combining them all into one really, really big expression that you can deal with.